What feels illegal in math but really isn't?
Cantor's diagonalizational argument, which he used to prove probably one of the most illegal sounding ideas in mathematics, that the infinite set of real numbers is larger than the infinite set of natural numbers. Now, before we get into the actual proof, first I want to help you understand the gist of his idea. Here I have set up a table with 4 rows and a number in each row. So the first row contains 3,794, the second row contains 6,781, and so on. Next thing we're going to do is highlight the first number in the first row, the second number in the second row, and so on. So it turns out that the number on this highlighted diagonal is 3,794, which you may notice is the same as the number in the first row. If I didn't want that, I could just add 1 to the first digit of the diagonal. So the 3 will become 4 and we'll end up with 4794. But now the number matches with the number in the fourth row, which is 4794. So now to make it different from the number in the fourth row, I can repeat the same process. I can add 1 to the second digit of the diagonal. So this new number, 4894, differs from the number in the first row and the fourth row. But what if I wanted to make sure that this number on the diagonal is different from all the other numbers? Well, I could do the same thing. I can add 1 to each digit in the diagonal. Now, if it's 9, what you can do is just go back to 1. You see, the thing I want you to be convinced of is that by following this process, we have created a number that is different from all the numbers in this table. It differs from the number in the first row, at least at the first digit. It differs from the number in the second row, at least in the second digit, and so on. Once you understand that, it will become easier to follow Cantor's diagonalizational argument for an infinite set. So now, instead of a finite table, we're going to imagine a table that extends infinitely to the right and infinitely to the bottom. You see, if the natural numbers and the real numbers had the same size, you would be able to pair them perfectly, much like the fingers on your hand to the toes on your feet. What Cantor did was that he listed all the natural numbers on the first column. The second column, he listed all the numbers from 0 to 1. But obviously he didn't literally list them. We're just imagining that because this is an infinite table, you have the ability to do that. And because they're the same size, all numbers from 0 to 1 and all natural numbers from 1 to infinity are on this table. Here's the genius. He used the same diagonalizational argument and showed that you can create a new number that is not on this table, which goes against our initial assumption. Hence, our initial assumption must be wrong. So they must not be the same size. This is proof by contradiction, which showed that the real numbers are larger than the natural.